For all of human history, the map of our existence was a local affair. The village, the kingdom, the continent, the world. Even when we first turned our eyes to the heavens, the cosmos felt manageable, a celestial sphere, a fixed canopy of stars, a clockwork universe orbiting our singular central sun. It was a story written on a page we believed we could hold in our hands. But the page was an illusion. The map was not a map at all, but a single, unreadable dot on the shore of an ocean whose size and shape defied all measurement. The true scale of the universe is not a number to be memorized. It is a profound and humbling silence, a void so vast it swallows not just light, but meaning itself. We built telescopes to bring it closer, only to watch it recede faster. We searched for an edge and found only a hall of mirrors. This is not the story of how we measured the cosmos. This is the story of how the cosmos, in its immensity, finally measured us. It is a story that begins not with a grand theory, but with a flicker, a single, pulsing point of light in the heart of a distant cloud, a flicker that would become a crack, and then a chasm, and then a revelation that would shatter our place in the universe forever. The first faint heartbeat of a new reality.
Welcome. You are watching Whisper Science. Make sure to subscribe and join us for more amazing science content. Now, let's move back to the video.
The first crack in the celestial sphere appeared not with a bang, but with a flicker. To the meticulous eye of Edwin Hubble, perched at the eyepiece of the Hooker telescope at Mount Wilson, this was not merely a curiosity. It was a signal, a cosmic heartbeat waiting to be decoded. These were Cephid, variable stars that rhythmically swell and contract, their outer layers breathing in a slow, luminous tide. And they held a secret, a password hidden in plain sight. Years earlier, a brilliant and largely unheralded astronomer named Henrietta Leavitt had discovered the key. While studying photographic plates at Harvard College Observatory, she noticed a profound pattern among these variable stars in the Magellanic Clouds. The rhythm of their pulse was a direct measure of their power. The longer the period between its brightest and dimmest phases, the greater the star's true intrinsic luminosity. A slow, majestic pulse meant a brilliant beacon. A quick, frantic flicker meant a far fainter candle. She had uncovered a fundamental rule, period luminosity relationship. It was as if each of these stars carried its own nameplate, announcing its true brightness to the universe. But to read it, one needed to know the language. Hubble, armed with Leavitt's key, began to listen. He measured the rhythmic dance of the Cephid in Andromeda. Its pulse was slow and stately. This told him its true luminosity, its absolute wattage. Then he measured its apparent brightness, how faint it seemed through his telescope. The difference between these two numbers, between how bright it truly was and how dim it appeared, could only be explained by one thing: distance. Light fades with the square of the distance traveled. It is a ruthless, unforgiving law of physics. The calculation was simple, but its implications were earth-shattering. The numbers placed Andromeda not as a nearby cloud of gas and dust within our own Milky Way, as had been long assumed, but as a system of stars impossibly far away. The answer was a number so vast it defied human experience. Nearly 1 million light-years. A distance so immense that the light he was seeing with his own eyes had begun its journey long before Homo sapiens had ever walked the Earth. The fuzzy nebula was in fact an island universe, a galaxy in its own right, a swirling empire of hundreds of billions of stars. Our Milky Way was not the entire cosmos. It was a single city in a metropolis whose borders had just vanished into infinity. In a single, quiet observation, the universe had grown 1,000,000 times larger overnight. The comfortable, contained cosmos of previous generations evaporated. Hubble, building upon the foundational work of Leavitt, had handed humanity its first true measuring stick, a cosmic ruler, and he immediately began to use it, turning his telescope to other faint, nebulous patches in the sky. He searched for and found more of these telltale, pulsating stars. Each one was a distant lighthouse. Each calculation was a revelation. Every fuzzy smudge of light resolved into another galaxy, each an immense, gravitationally bound island of suns, each separated from the next by a yawning, empty gulf of millions of light years. The cosmic page was not a page at all. It was a library. And Edwin Hubble, with Henrietta Leavitt's key in his hand, had just found the first shelf. He was no longer just an astronomer. He was a cartographer, mapping a continent whose shores had only just been discovered. The scale was incomprehensible, a vertigo of distance. These galaxies were not simply new objects in the sky, they were new worlds in the most profound sense. Each one could contain its own civilizations, its own histories, its own tragedies and triumphs, utterly isolated from our own by an ocean of space and time. The loneliness was palpable, the grandeur overwhelming. This was the discovery phase, a moment of pure, unadulterated awe. It was the end of one universe and the breathtaking and terrifying dawn of another. The new map of the universe was vast and silent, an archipelago of island galaxies, each a sovereign realm of starlight, adrift in a sea of black. But as Edwin Hubble and his contemporaries continued their measurements, a subtle pattern began to emerge from the silence. It was a pattern that would transform awe into disbelief, a discovery that would reveal the cosmos not as a static, majestic painting, but as a dynamic and terrifyingly violent event. The clue was hidden in the light itself. When starlight passes through a prism, it fractures into a rainbow spectrum, a barcode of color. Imprinted upon that barcode are dark lines, the unique fingerprints of chemical elements. As Hubble analyzed the spectral fingerprints of these distant galaxies, he noticed something peculiar. These fingerprints were shifted. The familiar patterns of hydrogen and calcium were not where they were supposed to be. They were stretched systematically toward the red end of the spectrum. This was the Doppler effect, the same phenomenon that causes a train's whistle to drop in pitch as it races away. The light was stretched because its source was moving away, receding into the distance. The initial assumption was one of random motion. Some galaxies would be moving toward us, appearing blue. Others would move away, appearing red-shifted, a chaotic cosmic dance. But the data refused to cooperate. With very few exceptions, the light from nearly every galaxy Hubble examined was red-shifted. They were all flying away from us. And the deeper he looked, the more shocking the correlation became. The farther away a galaxy was, the greater its redshift, the faster it was receding. The correlation was linear, precise, and undeniable. It became known as Hubble's law, a deceptively simple equation. Velocity equals the Hubble constant multiplied by distance. The universe was not simply expanding, it was expanding in a specific and profound way. This was the scientific shock. The scale of the universe was not a fixed volume, it was a constantly increasing one. The very fabric of space-time, the stage upon which the drama of stars and galaxies played out, was itself stretching. It carried the galaxies apart, like raisins in an infinitely rising loaf of bread. The image was serene, but its implications were revolutionary. It meant that if one could run the film of the universe backwards, all of those galaxies would rush together, closer, and hotter and denser, until they reached a point of infinite density, a singularity. The expansion implied a beginning, a moment of creation, a Big Bang, the concept of a center, a fundamental anchor for human thought, evaporated. From the perspective of any galaxy, on any raisin in the loaf, every other galaxy would appear to be receding. The center was everywhere, and the edge was nowhere. There was no privileged position. Our home galaxy was not the heart of the cosmos. It was merely a speck, fleeing from every other speck in a grand universal recession. This was a Copernican revolution on the grandest possible scale. It was a humbling and isolating realization. The shockwaves from this discovery rippled through the scientific world, forcing a dramatic reconsideration of Einstein's own work. He had famously inserted a cosmological constant into his equations of general relativity, a fudge factor, to keep the universe static, which he later called his greatest blunder. Hubble's observations rendered that constant unnecessary. The equations, in their pure form, had predicted an expanding or contracting universe all along. The universe was not, and had never been, still. It was born in motion, and it would die in motion. The question was no longer one of simple scale, but of destiny. Would this expansion continue forever, slowing under the relentless pull of gravity? Or would it eventually halt, reverse, and collapse back into a fiery big crunch? The answer, it seemed, lay in measuring the precise rate of this expansion, a number that would become the holy grail of cosmology, the Hubble constant, a number that would, in time, reveal an even deeper and more unsettling mystery. The expanding universe was now a fact, a fundamental pillar of modern cosmology. But a fact is merely a door, and behind this one lay a labyrinth of deeper and more intricate questions. The grand realization gave way to a more subtle, more meticulous pursuit, the pursuit of a number, a single value that would dictate the fate of everything. The Hubble constant denoted as HS, deceptively simple in concept. It is the rate at which the universe expands today, the number of kilometers per second that a galaxy 1 megaparsec away recedes from us. Yet to measure it, to pin down this fundamental parameter of existence, would require a feat of cosmic engineering. It would require building a ladder. This was no ordinary ladder. It was a cosmic distance ladder, a fragile chain of measurements stretching from the familiar streets of our solar system to the farthest, faintest glimmers of light at the edge of the observable universe. Each rung, calibrated with exquisite care, would allow astronomers to reach for the next. A single error, a slight misstep, and the entire structure would collapse into meaninglessness. The quest to measure H would become a story of perseverance, of ingenuity, and of a quiet, relentless war between precision and the profound emptiness of space. The first rung of the ladder was the most solid, the most grounded. It began in the inner solar system with radar. By bouncing radio waves off nearby planets like Venus and Mars, astronomers could measure their distances with breathtaking accuracy, using the simple, known speed of light. This provided a baseline, a fundamental unit of measure for the solar system. From there, they could employ the ancient technique of parallax, the same effect that makes a finger seem to jump back and forth when you view it, with one eye closed, then the other, as the Earth orbits the Sun. The apparent positions of the nearest stars shift minutely against the backdrop of infinitely more distant stars. By measuring this tiny angular shift, this stellar wobble, over 6 months, they could triangulate the distances to these stars with geometric certainty. This was the foundation, the solid ground upon which the entire ladder would stand. The next rung required a leap from the solar neighborhood into the galactic. This is where the Cepheid variables, those same rhythmic beacons that Hubble used, returned to center stage. But their use demanded a crucial and difficult calibration. Henrietta Leavitt had discovered the relationship between a Cepheid's pulse and its true luminosity, but the scale of that relationship was unknown. It was as if she had provided a map where the scale was missing. A slow pulse meant a brighter star, but how much brighter? To calibrate the scale, astronomers needed to find Cepheid's close enough to have their distances measured by another independent method. They needed a Cepheid whose distance could be measured by parallax. For decades, this was nearly impossible. The parallax shifts for even the closest Cepheids were vanishingly small at the very limit of technology. The breakthrough came from a relentless pursuit of precision. The Hubble Space Telescope, named for the man who first used these stars to redefine the cosmos, was tasked with this monumental calibration. Its sharp eye above the blurring atmosphere was finally able to measure the parallax of Cepheid's in our own galaxy, pinning down the period luminosity relationship with unprecedented firmness. The map now had a scale. These calibrated Cepheid's became the standard candles for the next leap. They were bright enough to be seen in nearby galaxies like Andromeda and the Virgo cluster. By finding Cepheids in these galaxies, astronomers could measure their distances directly. The latter now reached beyond the Milky Way. But Cepheids, for all their brilliance, have their limits. Their light fades into the immensity of space. To reach out further, to truly measure the expansion rate across vast cosmic distances, astronomers needed a brighter beacon, a cosmic supernova. They found it in the violent death of white dwarf stars. When a white dwarf in a binary system accretes enough matter from its companion to cross a critical threshold, it undergoes a thermonuclear detonation so precise, so uniform, that it always releases the same peak luminosity. This is a type Ia supernova, the ultimate standard candle. It can outshine an entire galaxy, making it visible across billions of light years. The strategy was elegant. Find galaxies that host both Cepheid variables and type Ia supernova. Use the Cepheids to measure a precise distance to that galaxy. Then observe the peak brightness of the supernova that erupted within it. Since astronomers now knew the true luminosity of the supernova and could measure its apparent faint brightness, they could calculate its distance independently. This cross-calibration, this handshake between the Cepheid rung and the supernova rung, allowed them to precisely calibrate the supernova themselves. Once calibrated, these brilliant explosions became the perfect tool to measure the expansion rate. Astronomers could now search for type Ia supernova in galaxies so far away that their redshift, their velocity of recession, was significant. By plotting their distances against their redshifts, they could directly measure the slope of the line. They could measure the Hubble constant. This, the distance ladder method, was one path. But there was another, a path that looked not outward into space, but backward in time. It looked to the very beginning, The cosmic microwave background radiation, the faint afterglow of the Big Bang, is a snapshot of the infant universe, frozen in time when it was just 380,000 years old. This radiation is not perfectly uniform. It contains tiny fluctuations in temperature ripples that are the seeds of all future structure, the galaxies and clusters we see today. By mapping these ripples with exquisite detail, as satellites like NASA's WMAP and the ESA's Planck did, cosmologists could use the power of physics to predict how the universe should have evolved. The standard model of cosmology, lambda cold dark matter, is a recipe that uses the ingredients of the early universe to predict the universe of today. The precise characteristics of the CMB ripples allow scientists to calculate the amounts of normal matter, and dark energy, and from that, they can predict what the Hubble constant should be 13.8 billion years later. For a time, these two methods, the local distance ladder and the ancient CMB, seemed to be converging. The Holy Grail was within reach. The number that would tell us the ultimate fate of the cosmos was being cornered. But science, especially cosmology, rarely offers simple answers. The universe, it seems, had one more shock in store. The two methods, both wielded with immense rigor and precision, began to stubbornly and persistently disagree. The local universe, measured by the painstakingly built cosmic distance ladder, was expanding faster than the pristine early universe measured by Planck said it should be. It was a tiny discrepancy at first, a faint whisper of discord. But as the measurements became more and more precise, the whisper grew into a shout. The number did not agree. The ladder and the blueprint were telling two different stories. This was no longer just a deeper investigation. It was the first tremble of a coming earthquake, a fundamental crack in our understanding of reality itself. The quest for a number had unveiled a mystery. For decades, the project of cosmology had been one of consolidation. A grand synthesis known as the Standard Model had emerged from the chaos of discovery. Its pillars were strong: the Big Bang, dark matter, dark energy. It was a framework that could explain the vast architecture of the cosmos, from the first spark of inflation to the large-scale cosmic web. The Hubble constant was meant to be the final precise number that would lock this model into place, a testament to humanity's growing understanding of the universe. But instead of convergence, the data brought a rift, a quiet, persistent dissonance that grew louder with every new observation. This was no longer a simple discrepancy in measurement. It was an escalation, a mystery deepening into a potential crisis. The two methods, the local and the primordial, were separated by an unbridgeable gulf of time. The cosmic distance ladder, built on Cepheids and supernova, measured the universe, as it is now a contemporary snapshot of expansion. The Planck satellite's measurement of the cosmic microwave background, by contrast, was a fossil. It revealed the universe as it was then in its infancy. The Standard Model provided the equations to connect that past to this present. It was the bridge between the two. The Hubble tension, the stubborn refusal of these two values to agree, suggested that perhaps the bridge itself was flawed, that something was missing from our fundamental recipe of the cosmos. At first, the natural assumption was error. Someone, somewhere, had made a mistake. The pursuit of this phantom error became an all-consuming focus for the community. Every rung of the cosmic distance ladder was subjected to merciless scrutiny. Was there a problem with the parallax measurements from Gaia, the spacecraft tasked with mapping the Milky Way? The data was checked and rechecked. It held firm. Were we misunderstanding the Cepheids themselves? Perhaps dust interstellar material drifting between the stars was dimming their light and fooling our distance calculations. The Hubble Space Telescope, and later the James Webb Space Telescope, were tasked with observing Cepheids at longer infrared wavelengths, where dust is more transparent. The result was not a resolution, but a confirmation. The James Webb Space Telescope's first observations for this purpose, with its stunning infrared clarity, only served to reinforce the distance ladder measurement. The error, if it existed, was not being found. On the other side, the CMB measurement from the Planck satellite was a masterpiece of precision. Its map of the infant universe's temperature fluctuations was exquisitely detailed. The parameters derived from it were self-consistent and powerful. To suggest it was wrong was to challenge one of the most successful experiments in the history of science. The model it supported, lambda CDM, could predict the distribution of galaxies, the clustering of matter, the very evolution of the cosmos, with stunning accuracy. And yet the number disagreed. The tension was not easing with better data. It was hardening. What was once a faint 2 sigma hint, in the language of science, this was no longer a hint. It was evidence that something was profoundly wrong. This was the escalation, the shift from a technical problem in measurement to a potential crisis in physics. The two most powerful, independent methods for taking the universe's vital signs were giving two different answers. It was as if a doctor measured a patient's pulse at their wrist and their neck and found two different heart rates. The conclusion is unsettling. Either the instruments are broken, or our understanding of the body itself is incomplete. The scientific community fractured into camps. Some held fast to the local measurement, trusting the direct rung-by-rung approach of the distance ladder. Others placed their faith in the pristine physics of the early universe and the power of the standard model. A third group began to entertain a more radical possibility, that both were right, that the discrepancy was real, that the Hubble constant measured locally was genuinely different from the value extrapolated from the ancient past. This could only mean one thing: the model connecting the past to the present, the lambda CDM model, was missing an ingredient, or perhaps one of the peekaboo we thought was constant was not. The mystery deepened the more it was studied. It wasn't just Planck and the distance ladder. Other probes began to weigh in, adding layers of complexity. Measurements from the Atacama Cosmology Telescope, another CMB instrument, initially seemed to align more closely with Planck, supporting the lower value. But later analyses introduced their own subtle uncertainties. Studies of the cosmic distance ladder, using different standard candles, like the brilliant but rare tip of the red giant branch method, began to yield results that intriguingly fell somewhere in between the two opposing values. It was as if the universe itself was refusing to be pinned down. The simple question of how fast had opened a Pandora's box of existential questions. The escalation was complete. Cosmology was no longer in a period of answering questions. It had entered a new golden age of questioning answers. The comfortable era of the standard model was over. The era of the unknown had begun again. The tension was no longer a whisper in the data. It was a thunderclap echoing across the field of cosmology. A 4, 5, now even 6 sigma discrepancy between the local and primordial measurements of the universe's expansion is not an error. It is a signal, a message from the cosmos that our understanding, however elegant, is incomplete. With the scaffolding of the standard model now shaking, theorists began to venture into uncharted territory. They began to speculate. This is not wild guesswork, but a rigorous, mathematically grounded exploration of the possible. If the bridge between the early universe and the present day is broken, what could have built a new one? The proposals are as breathtaking as they are radical, each one peeling back a layer of reality to suggest a cosmos far stranger than we had ever imagined. One of the most compelling lines of inquiry points a finger at the most mysterious component of the universe: dark energy. In the Standard Model, dark energy is embodied by Einstein's cosmological constant, a smooth constant energy permeating the vacuum of space, whose repulsive gravity drives the acceleration of the expansion. But what if dark energy is not constant? What if it evolves? Theories of early dark energy propose that a new form of energy field, similar to dark energy, was active in the first 100,000 years after the Big Bang. This transient energy would have subtly altered the rate of expansion in the universe's infancy, changing the sound waves that later became the frozen ripples in the cosmic microwave background. This would mean the Planck satellite's measurement of the early universe is correct, but our interpretation of it is wrong. The model we use to extrapolate from that early state to today would need to account for this phantom energy that came, boosted expansion briefly, and then vanished. It would make the early universe expand faster than we thought, meaning it would take less time to reach its current size, thus requiring a higher expansion rate today to match. This could neatly close the gap, but at the cost of introducing a fundamentally new and ephemeral cosmic ingredient. Other speculations dive into the dark sector itself. Perhaps dark matter, the invisible scaffolding upon which galaxies are built, is not that simple, cold, and non-interacting substance we believe it to be. What if dark matter particles can interact with each other or with dark energy through some unknown force? Or perhaps a fraction of dark matter is dark radiation, extremely fast-moving particles that would have provided an extra kick to the expansion in the early universe, again altering the conditions Planck observed. Another proposal suggests a phantom dark energy whose strength grows with time. This would mean the acceleration we see today is not a constant, gentle push, but a force that is increasingly dominating the cosmos, leading to a future big rip where even atoms are torn apart. Such a model could potentially account for a faster current expansion rate. Perhaps the most mind-bending theories challenge not just the ingredients, but the very laws of physics themselves. Einstein's theory of general relativity, the foundation of modern cosmology, has passed every test thrown at it, from the bending of starlight to the detection of gravitational waves. But it has never been tested on the largest possible scales across the entire observable universe. Could gravity itself work differently over these vast cosmic distances? Some modified gravity theories propose that the force of gravity weakens slightly over cosmological scales. This would mimic the effect of dark energy, but could also alter the relationship between the early universe's properties and the expansion rate we see today. It is a profound proposition that our understanding of gravity itself, the force that sculpts the cosmos, is only a local approximation. Then there are the most speculative and profound of all ideas. The Hubble tension might be the first empirical evidence that we are not living in a single uniform universe. The concept of a cosmic void suggests that our Milky Way galaxy might reside in a vast billion light-year wide region of space that is less dense than the average universe. If we are in an underdense bubble, the local gravity would be weaker, allowing space around us to expand faster than the global average. Our measurements would be correct, but only for our local neighborhood. We would be like islanders who, having only ever known a calm lagoon, believe the entire ocean is still unaware of the raging storms beyond the horizon. This idea dovetails with an even more radical interpretation. The Hubble tension is evidence for a multiverse. In the eternal inflation theory, our observable universe is just one bubble in a frothing, infinite multiverse. Each bubble has its own unique physical constants, its own local laws of physics. The laws we measure: the strength of gravity, the mass of the electron, the value of the Hubble constant, may not be universal truths. They may be provincial bylaws unique to our bubble. The tension, then, is not a problem to be solved, but a fingerprint, a clue that the constants we hold sacred are not constant at all, that beyond the veil of our observable horizon, the rules are different. We are not measuring the universe, we are merely measuring our room within it. Each theory, from evolving dark energy to modified gravity to the multiverse, carries its own philosophical weight. They ask us to relinquish a little more of our cosmic certainty. They transform the Hubble constant from a simple number into a Rosetta Stone, and we are only just beginning to understand the language it is written in. The speculation is not an admission of failure, but the highest form of scientific creativity. It is the sound of physics, listening to the universe and preparing to write a new chapter. The speculations hang in the air, vast and shimmering like mirages. But cosmology is not a discipline of philosophy alone. It is a science of data, of light, collected one photon at a time. The grand theories, the exotic proposals of early dark energy and modified gravity must face the tribunal of observation. They must make predictions, and those predictions must be tested. This is the era we have now entered, the great cosmic inquiry. Around the world and above it, a new generation of instruments, telescopes, cameras, satellites have been designed and deployed. They are not merely larger versions of their predecessors. They are different kinds of eyes, engineered to see the unseen, to measure the immeasurable. Their sole purpose is to hunt for the source of the discord, to find the flaw in the model, or to confirm a new reality. The first line of attack is to reinforce the cosmic distance ladder, to eliminate any lingering doubt about the local measurement. The James Webb Space Telescope, with its pristine infrared vision, is now conducting a relentless audit of Hubble's work. It is peering through the obscuring dust of nearby galaxies, observing the same Kifid variables that Hubble studied, but with a clarity that was once unimaginable. Each flickering star is being measured with unprecedented precision. Is there a systematic error in the optical measurements that has fooled us for decades? JWST's infrared data will provide the answer. It is a painstaking pixel-by-pixel, star-by-star process of verification. The goal is not to prove one value right, but to ensure the measurement is ironclad, to leave no shadow of a doubt that the local universe is truly expanding at this faster rate. Simultaneously, a completely independent method is being pursued from the ground. The Vera C. Rubin Observatory, with its car-sized digital camera, will soon begin a decade-long all-sky survey. It will not be looking for a few key stars, but mapping the positions and motions of billions of galaxies. Within this immense cosmic cartography lies another way to measure expansion through baryon acoustic oscillations, BAO. These are the fossilized imprints of sound waves, that raced through the plasma of the early universe. They left a faint, preferred scale of separation in the way galaxies cluster, a standard ruler etched into the fabric of space-time. By measuring the apparent size of this ruler at different epochs of the universe, astronomers can trace the history of expansion directly. This method, straddling the local and the distant, provides a crucial third perspective, independent of both supernova and the CMB, to probe the dark universe. Directly new missions are launching. The ESA's Euclid Space Telescope is now orbiting the Sun, its gaze fixed on the shapes of galaxies. It will hunt for the subtle distortions caused by dark matter bending spacetime, a phenomenon known as weak gravitational lensing. By mapping the distribution of dark matter across 10 billion light-years, Euclid will precisely measure how the cosmic web has clumped over time. This growth of structure is exquisitely sensitive to the expansion rate and the properties of dark energy. Any deviation from the predictions of the standard model, any hint of evolving dark energy or interacting dark matter will be revealed in this vast three-dimensional map of the invisible. NASA's upcoming Nancy Grace Roman Space Telescope will combine the powers of both Hubble and Euclid. It will perform a supernova survey far larger and deeper than any before, discovering thousands of distant type Ia explosions to build the most robust distance ladder ever conceived. At the same time, its wide-field lensing surveys will rival Euclid's. Roman is designed to be a machine for precision cosmology, built specifically to solve mysteries like the Hubble tension. And still, the primordial universe is being re-examined. The Atacama Cosmology Telescope and the South Pole Telescope arrays of ultra-sensitive detectors in the world's driest and coldest deserts are creating new, ever more detailed maps of the cosmic microwave background's polarization. These patterns, finer than the temperature fluctuations, hold the key to understanding the universe's first, second. They could reveal the signature of primordial gravitational waves or the faint echo of that proposed early dark energy that might have briefly flared into existence. This is the scientific process at its most magnificent. It is a multi-pronged global effort, a symphony of technology and theory. Each instrument plays a different note, each survey a different movement. The James Webb Telescope, the Vera Rubin Observatory, Euclid, Roman, the polar telescopes, they are not competitors. They are a single distributed instrument, a network of perception aimed at a single goal: to listen to the message the universe is sending. The data is now flooding in, petabytes of it. Within this deluge of light and information, hidden in the subtle correlations and tiny discrepancies, lies the answer. The tools are now listening. The cosmos is about to speak. And so we find ourselves here, at the edge of a known world, peering into a mist that has refused to clear. The quest began with a simple desire to measure, to place a ruler against the cosmos and etch a number onto the tablet of human knowledge. We sought a constant and found instead a question. The Hubble constant, that single number meant to define the fate of all things, has become a symbol of something far greater. It is no longer an answer, but a doorway. The true scale of the universe, we now understand, cannot be captured by a statistic. It is not contained in the staggering figure of 93 billion light-years, the diameter of our observable bubble. The true scale is the depth of the mystery itself. It is the humbling realization that the laws we discover, the constants we hold as inviolable, may be local, ordinances, temporary truths, in a single neighborhood of a reality so vast, it redefines vastness with every new revelation. We built telescopes to extend our senses, and they have instead extended our ignorance. We have seen so much, only to understand how much there is left unseen. This is not a failure of science, it is its highest achievement. The universe is not a puzzle to be solved, but a story to be read. And we are only on the first page. The Hubble tension, this persistent discord between the ancient and the modern, is the first sentence of a new chapter. It tells us that the story is more complex, more bizarre, and more beautiful than the standard model could ever contain. It hints at forces, yet unnamed, at dimensions, yet unfelt, at a history, yet untold. There is a profound emotion that accompanies this realization. It is not the loneliness of a tiny planet adrift in a void, but the quiet awe of a consciousness that can perceive the void itself. We are the universe become self-aware. We are the means by which the cosmos measures its own expansion, questions its own nature, and ponders its own origin. Our struggle to pin down a single number is the universe through us struggling to understand itself. The poetic irony is absolute in our relentless pursuit to explain the cosmos. We have been led to the brink of the inexplicable. The tools we built to bring the heavens closer have revealed a horizon that forever recedes. The map we sought to draw has turned out to be a single, intricate, and unique fingerprint on an infinite tapestry. We have not found the edge, we have found that there is no edge. We have not solved the mystery, we have deepened it. So the journey does not end here. It begins again. Every new telescope, every new dataset is not a step toward a final answer, but a step into a deeper wonder. The true scale of the universe is not its size, but its capacity for mystery. It is the endless unfolding of question after question, a cosmic bloom that never quite finishes opening. And we, fleeting and fragile on our pale blue dot, are granted the privilege to witness it, to feel the awe, to sit with the silence, and to continue the eternal human act of looking up and wondering. The measurement was never the point, the wonder was.